So good morning, everybody. Welcome for this new seminar. Today, we will have the talk by Dr. José Carlos del Toro. He will talk about the art of astrophysical measurements and elementary lectures on photon counting and simultaneous. So José Carlos del Toro Iniesta was born in Cartagena in Spain in 1960, and he studied physics in the University of Granada, the first 3 courses, and then in La Laguna in Spain for major astrophysics. He's a CSIC research professor at the Instituto de Astrofísica Andalucía here at our house in Granada, and he's a specialist on solar magnetic fields. He got a PhD degree from the University of La Laguna and carried out a part of his career at the Instituto de Astrofísica in Canarias, including a sabbatical year at the Lockheed Palo Alto Research Laboratory. Since 1998, he belongs to the staff of our house from IAA, and he has published some 180 papers on scientific journals and meeting proceedings. Has been editor of 2 books and author in 2003 of another one entitled Introduction of Spectropolarimetry, published by Cambridge University Press. He has taught advanced undergraduate courses at the University of La Laguna and postgraduate courses in Austria, Japan, Germany, and United Kingdom, United States, and Spain. He is co-investigator of the stratospheric balloon Sunrise mission. He is an associate investigation of the IAA instrument of the NASA's Solar Dynamic Observatory mission. He is co-principal investigator of SOFI, magnetograph of the European Space Agency's Solar Orbiter mission. He is principal investigation of the 2 magnetograph of and co-principal investigator of SISP spectropolarimetry of the Sunrise 3 mission. He has been director of our house from 2004 through 2007. He has been the Spanish national manager for space research of the Spanish Research Agency from 2017 until 2019. So thank you very much, José Carlos, for this seminar, and the floor is yours.
Thank you very much, René, and thank you very much, you all, for attending this talk that I consider more a lecture than a regular talk. And this is because a few months ago, I was invited to write a chapter on solar magnetograph and tachographs for a book entitled Observing Photons in Space for Springer. And when I wrote that chapter with my friend and colleague, Valentin Martinez-Pillet, current director of the American National Solar Observatory, and future director of the IC, I realized that the topic was of interest for you all, because somehow solar magnetographs or spectropolarimeters are kind of an epitome of all kinds of astrophysical measurements. So in an attempt to battle the usual belief that we measure masses, velocities, magnetic fields, temperatures of heavenly bodies, I want to stress that this is not true, that we measure only photons. In an attempt to dismantle the common belief that we solar physicists have an excess of photons in our daily life, I want to stress that this is not true, and I hope you will finalize this talk convinced that we are as much photon-starved as any observer looking at the confines of the universe. And in an attempt to motivate you to have a look, to have a grasp on the means you have available at your disposal when looking at the sky, I prepared this talk that I hope you will enjoy. Oh, now, why? Okay. So, have you ever dared to evaluate how many photons reach your detector when you are pointing the telescope to the sky? Are you sure that all the effects the spectrograph, if any, is adding to those photons when you are analyzing them? Do typical rules of image formation apply when we carry out this image formation analysis with polarized light? Well, these are a few questions that are typical for researchers when trying to design instruments, okay? These instruments are later constrained, not by physical, but by spurious constraints that can come from technology or even budgetary and administrative limitations. So, of course, I won't enter into details of those constraints and focus in physics, okay? So, I said that spectropolarimetry is an epitome of all kinds of measurements because we are doing everything an astronomer can do with light. We are measuring the spectrum of the polarized light, okay? Here you are going to see in this movie how we are carrying out a 5D spectroscopy, and I like to say this because I like to brag in front of you guys, night astronomers that are very proud of 3D astronomy. So this is 3D because you have two spatial dimensions and one wavelength dimension, but we are adding the fourth dimension with polarization. Here you can see how when we have cut this cube at a given position in space, we are recording the spectrum in 4 different ways corresponding to the 4 Stokes parameters of light. If instead we cut this cube at a given wavelength, we can imagine the sun or any other object in all 4 Stokes parameters. So this is a wealth of information which is at our disposal, at your disposal, but from time to time, we have to renounce to analyze the polarization or even the spectrum of light. I said 5D spectroscopy, and these are only 4 dimensions. The 5th dimension is time, because typically we carry out measurements of all those 4 dimensions in a time series, because heliosseismology is our only means to probe the interior of the sun. So the work we carry out typically is kind of involved, but let's analyze step by step what we are doing. Certainly, we need tools. For imaging, we need an imager, so we need a telescope or photon collectors and cameras, okay? As a spectrometer, we can use a spatially scanning spectrograph, cutting the cube at different slices, spatial slices, okay? Or a filter graph, just tuning the hypercube at different wavelength positions, okay? We also need polarimeters, and eventually we need data processor like on board our instruments, as is the case of our polarimetric and helioseismic imager aboard solar orbiter. All these pictures are a few examples of instruments and subsystems of instruments developed by our team, the solar physics group of the IAA, which leads the so-called Spanish-based Solar Physics Consortium, a consortium of 5 public institutions in Spain, which are working for more than 20 years, and including, besides IAA, INTA, University of Valencia, the Instituto Ignacio de Arriba from the Technical University of Madrid, and the ISC. So these interinstitutional team is working, producing spectropolarimeters, well, as I say, for more than 20 years. So the basic goals when an astronomer is going to observe are typically get the best spatial resolution, best spectral resolution, best polarimetric sensitivity at a minimum time. Okay. And of course, you cannot do everything at the same time. And this is already heralding why I call the art of astrophysical measurements, because compromises must be applied between these goals. Okay, but we need to go to we look for spatial resolution because the critical scales of solar phenomena take place at scales closer or even smaller than the mean field path of photons. We are speaking about tens of kilometers. The important physical phenomena like radiation transfer include like Doppler effect, Zeeman effect, Handler effect, scattering, and all other physical phenomena occurring at the star leave their fingerprints in the spectrum and in the polarization state of light. And we have to hurry up and do measurements in shorter times because the sun is evolving at many time scales, and because there are correlations between image quality and integrity with time. Because if we are taking too long for having a single data set, then the sun was one at the beginning and another one at the end. Okay, so these are the basic goals that we typically have to trade off with. But the business, the astronomical business, the astronomical measurement is counting photons. Okay, we are just simple mere photon counters, and let us digress a little bit on what's going on with those photons. Here you have the surface of that zone of the sun imaged by a single pixel of my detector. Okay, so seen from my detector, from the telescope, this surface is subtending this solid angle. Okay, it is emitting light in all directions, but only those rays within this cone of solid angle omega s reach the telescope and then the pixel. Okay, so and these surfaces are inclined with respect to their respective normals by angles theta and theta prime. So what I want to know certainly is how much energy is emitted in the sun. And what I know is what I measure, the energy detected by my pixel. So let us calculate both. And we have this in here. So E is in a given bandwidth, wavelength bandwidth. This is the energy emitted by the sun, and this is the energy received by my pixel. Okay, I have to integrate the corresponding things. Tx is the exposure time of my single shot image. Okay, And here, I lambda and I prime lambda are the typical specific intensities. That is, energies per radiated or received, per unit solid angle, per unit normal area, per unit wavelength, and per unit time. Okay? If there is nothing between the emitter and the absorber, E and E prime should be the same, should be equal, must be equal. Okay? Then if I carry out some change of variable in the integrals, I can subtract these two to get a 0. And this can only be 0 if and only if I is equal to I prime. Because the other possibility is that either the theta or theta prime is 90 degrees, but this has no physical meaning. So in the absence of sources and sinks between my emitter and my absorber, specific intensity, so energy per solid angle, per normal surface area, per wavelength, and per time, per unit time, is the same. And this is great. This is great because it allows us to evaluate the energy emitted by the sun by using the specific intensity I measure. Okay? If I change energy by the product of number of photons and the energy of each of them, then I can calculate and get this expression where you can really see that there are more photons in the red than the blue. So bad news if you want to go to the ultraviolet. This is simple photometry, okay? So independently of the energy emitted by the source, if you are in the blue, you have more difficulties. D and D are the primary and secondary the diameters of the primary and secondary mirrors of the telescope. Okay, and omega pixel is just the pitch of my pixel. Okay, great. Now I have to calculate the number of photons, but this has not taken into account any effect introduced by the atmosphere, by my instrument, including the telescope, etc., and so on and so forth. And certainly, the size of the telescope aperture is not the only limiting factor. So the scene in ground-based observations or spacecraft data introduce blurring in my image. Aberrations of optical components can deteriorate the image quality and even the throughput. Stray light reduces contrast. Detectors can introduce spurious signals. So in summary, an overall assessment is mandatory. And this assessment is provided by the point spread function of all the chain, all the system transmission between the emitter and the receiver. Okay, so we better deduce the point spread function, the impulse response of our system in order to understand our images. If P is this response function, then the observed intensity as a function of space is the convolution of the original, the real solar intensity, and the normalized point spread function. Tau is simply the monochromatic throughput. Okay, so but if I want to get the fractional limit, because I'm interested in the best spatial resolution, then this determines directly the size of my pixel. My pixel should be a fraction of lambda over d, according to Rayleigh criterion. Okay, so that the former formula can be written as in here. And this is very interesting So the dependence on lambda is even stronger. So UV is very difficult. UV is very difficult, and infrared is better. But there is a significant curiosity here, because imagine you have an off-axis telescope, so that the secondary does not make any shadow on the primary. In such a case, this is 0, and then the number of photons is independent of the size of your telescope. Okay, and this is why we are photon starved, because although we use also on-axis telescopes, this decreases the effect of the diameter is very small, and this is natural and easy to understand, because a larger telescope increases the number of photons, but also decreases the size of the area you are imaging on its pixel. Okay, so that we in solar physics measure the same photons of a barely resolved star with the same physical parameters, with the same temperature, pressure, etc. Okay, so this is one of the things that I wanted for you to realize. Then, if we measure photons, we have to do it well. How we do well good photon counting? Just by taking care that the noise is small. As simple as that. But noise is cumbersome. Noise has a term which is independent of the signal. Here, it has a quadratic term which is dependent on the dark current signal, and here a quadratic term in radial signal, the signal we want to keep, okay, and to keep higher than the noise, okay. So this is radial noise. This is offset fixed pattern noise, which has to do with the gain of columnar amplifications of the detector. This is quantization noise, but these are typically in solar observations. These are small. Okay, so the point is in here. Well, those things related to dark current are in principle easy to correct, because you can take independent measurements with by obscuring your camera, and then you can take this out of your signal. But the point is that you have quadratic terms in the signal that must be avoided. So if we want to go to a photon noise regime where the noise is of the order of the square of the noise is of the order of the signal, or the noise is the square root of the signal, then we have to be very careful, and then fill the photon well of our pixel enough as for having this very small compared to my signal, but to have it empty enough as for those quadratic effects to be negligible. Okay, and this is also part of an art, because there are no golden rules for that say, hey guy, you reach 1/3 of your photon well, and then that's all. No, you have to carefully adjust your your instrument in order to have the well filled enough and empty enough as well. So in the end, if we are successful, and then our signal to noise is proportional to the ratio of the number of photons. I have introduced in here the quantum efficiency of my detector, which was not taken into account in my former formula. And I am using the lowercase letters for a reason that you will understand later. Okay, so my goal should be to reach the photon noise regime, and in such a regime, my signal to noise ratio is of this order. Then let's go for spectroscopy. So spectrographs, in order to cover that for the cube, okay, spectrographs have to scan across the space. Okay, I have to put my slit step by step in different positions over the sun, and then reconstruct the spectrum in the other direction. Filter graphs, instead, tune between different wavelengths. We are cutting the cube at different wavelengths and imaging at each wavelength. But both are based in interference. Interference have orders, and then both need another sorting pre-filter. So the normalized response, spectral response of my system, G, is the product of the pre-filter transmission and the pre-filter of the filter graph transmission, or the spectral PSF of my spectrograph. With such a nomenclature, then if I would only be doing spectroscopy, I would take the original intensity, convolve with the spectral response, and get the observation. But if I want to do imaging spectroscopy, then I have to also convolve with my spatial PSF. Okay? Now, polarimetry. Polarimetry is as common to electromagnetic radiation as intensity or spectral depends on wavelength. Okay? But now life gets more complicated because we have to measure 4 quantities. All 4 Stokes parameters that here are represented by a column vector. T is transpose. Okay, I is the intensity. Q, the difference in intensity between linearly polarized light at 0 and at 90 degrees. U is difference between linearly polarized light at 45 and 135 degrees. And V is the difference in intensity of circular right-handed and left-handed circular polarizations. These 4 quantities are bounded by the Chandrasekhar's relation, which is just the Minkowski's metric of special relativity. So the intensity is always larger than polarization. Okay, when these 2 members are the same, we say that the light is completely polarized. In some other cases, it's partially polarized. And when all Q, U, and V are 0, then we say that the light is natural or completely unpolarized. Okay, I said our lives get more complicated because now, since we have to measure 4 quantities, we need at least 4 measurements. Okay, we need to form at least 4 linear combinations of I, Q, U, and V. The shape of the coefficients in front, some of you have already guessed that are reminiscent of being the elements of the first column of the polarimeter matrix. But this is another stuff that we cannot enter today. Okay, so our measurements for polarization are not measurements of intensity alone, are linear combinations of all four Stokes parameters. Okay, so polarimetry is differential photometry. Q is difference between 0 and 90. U is difference between 45 and 135. V is difference between right-handed and left-handed. Okay, and differential photometry is much more riskier than regular photometry, because imagine any spurious effects, any variation of the sun between the first measurement and the second measurement, then introduces spurious signals that are damaging my result. So I have another difficulty when doing polarimetry. But and also I wanted to remark that the conservation of energy of the invariance of specific intensity we saw in the first considerations on photon counting are indeed a special case of a more general one. When you are considering the transfer of polarized radiation, which is much more general than the former analysis, then you have this radiation transfer equation. J is the emission, K is the propagation matrix. Okay, then when the propagation matrix and the emission are 0, which is when in the absence of sources sinks by refringent dispersive media between the emitter and the absorber, then this is 0, so that the full Stokes vector is conserved. So not only energy is preserved, but also angular momentum. The conservation of Q, U, and V speak about the angular momentum of the photons. So just for the non-experts to have a grasp on what we are talking about, here I show you the spectrum of these two lines, which are 1 angstrom apart, 1 angstrom apart. This is Stokes I, Q, U, and V. Certainly the differences are giving us physics from the sun. But what I wanted to remark is that, as you can see, it's much more difficult to measure Q and U than I and or V, because noise, the dashed lines, noise is higher. And this is pure consequence of the way we measure polarization. Okay, so the smaller this noise, the better, because we could detect much more real signals. Okay, so my battle in doing polarimetry is the same as for doing photometry or spectroscopy. I have to reduce signal to noise, increase the signal to noise ratio, have to reduce noise. Okay, without entering into details, we have realized that the smaller Q over I, U over I, and V over I, the more precise my parameter will be. Okay, so the precision, the polarization precision, is kind of an inverse of the signal to noise ratio. If for each of the 4 Stokes parameters, 0, 1, 2, and 3, for I, Q, U, and V, I define the signal to noise ratio as in here. So at the continuum wavelengths, I take Stokes I and divide over the variance of my signal. And this can be considered the polarization precision, so the inverse of this quantity. Okay, so the smaller the piece, the better my parameter. It is possible to demonstrate that there can be parameters that fulfill these conditions for the so-called polarization efficiencies. Polarization efficiencies are directly related to precision. So the larger the epsilons, the more precise my polarimeter. And it is also easy to see that the signal to noise ratio in Q, U, and V are smaller than in I, because epsilon I is always smaller than epsilon 2, as you can see from this relation. Okay, so it is much more difficult to measure Q, U, and V than simple stop sign. Well, polarimetry has not only that difficulty of measuring several measurements, but it has also instrumental problems. Okay, for instance, one can demonstrate that revolution symmetry in the optical path preserve the polarization state of light. So do not introduce any spurious polarization to my measurements. However, this is only exactly true at the axis of the path. Then there are contributions of my instruments which increase even when which increase with the size of the telescope aperture. So if I want to get details, very small details in polarization, that property of revolution symmetry cannot help, and I must calibrate independently of having revolutionary symmetric telescope or not. Spectrographs introduce polarization. Spurious polarization have to be taken into account. Filter graphs introduce polarization. Okay, so all this stuff would imply that a specific treatment of my point spread functions and filter transmissions, as I used before, had to be treated differently for polarization. But as far as I know, nobody has ever made this. And we assume that all those possible effects, we hope that they are negligible and forget them. So this is, in my opinion, a fertile field of research right now, theoretical research. And then with that assumption, my observation for a given wavelength is the convolution of my linear combination of Stokes parameters convolved with the filter, with the spectral response and the point spread function. Here is a J index. Remember, we need at least 4 such equations. Okay, so I have a system of equations. I have to invert it in order to deduce I sun, Q sun, U sun, V sun. Certainly, no inversion is perfect, and then some errors get in the form of so-called crosstalks in our results. So some mixture of all 4 Stokes parameters appear, and we have to take care of those mixtures. Well, then when I go to real instruments, I have to make a decision. I have to trade off between the different goals, because for instance, I can increase my spatial resolution, but then I get rid out of photons. Or the same with spectroscopy. If I reduce my bandwidth, then I run out of photons. Or if I take too much time, spatial or spectral integrity are forgotten. Not to say that the different spectral lines that we select speak of different physical phenomena of our object. So this is a cumbersome decision, system of decisions you have to carry out. So typically, image quality is made so that we approach the diffraction limited condition, which is obtained for a Strel ratio larger than or equal to, greater than or equal to 0.8. You may need it, you may not need it, but if you need it, then other constraints may destroy your design, and just because you have to take into account some electronics, firmware, software, thermal effects, etc. And then you result in having imperfect observations that have to be corrected for afterwards. So you better take care and determine the PSF and the transmission profiles of your instrument. Optimizing the spectral resolution, as I said, cannot be minimize the bandwidth, because you need some photons to make your measurements. So a balance must be found, but a balance which is not defined. Again, kind of an art is needed in this trade-off. But our business is of counting photons, and we better go again to the formula. Okay, so we have all these quantities, and we have to tune the values of our design in order to get the best compromise among them. Increasing the quantum efficiency of the detector has no drawbacks. So the higher, the better. So this is the only thing you can do without thinking. But lambda zero, so the number of photons increases with lambda zero or with lambda to the third for diffraction limited instruments. So if we go to UV, we run out of photons, and then our signal to noise goes down, our parametric precision goes down. So UV spectroperimetry is very, very challenging. If we make our system faster in the optical jargon, if we increase the solid angle seen by our pixels, okay, we certainly are able to capture more photons. This is good. And even systems with those big apertures, these acceptance angles can be less sensitive to temperature. However, if it is too large, you lose spatial resolution, okay? Or you lose spectral resolution, because the size of the slit in the spectrograph is also governing the spectral resolution. So you have to take very much care on how to define, how to select the solid angle which sees your pixel. Diameter of the telescope. Well, increasing the aperture is always the best. It's always good. But remember, for diffraction limited telescopes, the help is not very much. It is not very high, and maybe of little help. Here, lambda wavelength, if I increase my bandwidth, I get more photons. But the details in the spectrum that are telling me the physics of my object can be lost. So again, art. And last but not least, time. Tx, remember, was one single shot. Okay, one single frame shot. In principle, the longer Tx, the better, because of photons. But it should be short enough as for freezing the scene or the jitter of my instrument. Okay. Then if I cannot increase Ts very much, then I have to be clever enough and take several shots with a small Tx and add it on top of each other. Accumulate Na shots in order for my signal to noise to increase with the square root of the number of those individual shots. Okay. But another constraint comes from the dynamics of the sun or the object. So I cannot spend a total time larger than the typical time scale of my object. If I'm observing a phenomenon in the sun that is taking place with typical scales of 10 seconds, and I take 2 minutes, then I forget any insight from that phenomenon. Then I have to take care of these, and this total time is the effective time, which is the number of the single shot time times the number of polarizations times the number of accumulations and times the number of wavelengths I'm taking. But I have to add an overhead time, because there is no ideal instrument that doesn't take any time in changing between one measurement and the other, between one wavelength and the other, or by rastering this space. Okay, so in the end, I have to define a duty cycle which should be introduced in this relation. In instruments like IMAX or TUMEC, both fully Spanish, we carry out so-called dual beam polarimetry, and we can increase by a factor square root of 2 the signal to noise ratio. So you have seen how trading off is a real task and a real art in analyzing our measurements. So signal to noise is at the very heart of our measurements, of any astrophysical measurement. You can increase this and resign to this or that other, but it has consequences on all directions. Okay, so there is no mathematical rules for designing the best instrument. Okay, and we have to better design our instrument according to our scientific goal, to the physical phenomena that we are going to study. Well, this is only for measuring photons. Okay, I haven't said anything of translating those photons to the real physics we are looking for. So my final message: mistrust of any arrogant colleague that says I measure the masses of this black hole or whatever, because this is not true. You guys have measured photons, and maybe you've done very well, but for measuring those photons, you have made many trade-offs, compromises, and so on and so forth. And for the interpretation of these photons into masses, temperatures, magnetic fields, etc., the number of assumptions is even bigger. So be humble, my friend, and thank you very much.
Thank you very much, José Carlos. So, questions?
José Carlos, thank you very much for this great introduction to the black art of photography. I assume that the detector that you're using is a type of CCD or CMOS, where you actually the well is filled by electrons, not photons.
Sure.
Okay.
Sure.
Right. So we have recently been using a single photon detector to measure some computational methods, some other sources. And we get we use a time resolution of 1 microsecond, so we can actually count single photons.
Mm-hmm.
How, and I guess we can do similarly to count single photons spread over all the wavelength range and all the spatial directions and all the polarimetry values. And can you do that with single photons and then add up to the exposure time that you like or to the resolution that spectral resolution that you like?
This type of detectors are not included in this analysis. Okay. Well, the first thought that comes to my mind is that for measuring one polarized photon out of 10,000 or of 100,000, as for the sun, you would need to be waiting quite a lot of microseconds time of your detector, etc. But I think all the reasonings should be the same. Should be exactly the same. You are counting single photons, but I don't know which kind of noises you are risking at. And you certainly have to go and carefully analyze which is the noise associated with your detection. Okay.
More questions?
When you mentioned the compromise for the pitch, the pixel pitch, what happens when you open it wider and you get the photons coming from the side? Is it the same behavior of photons coming from a larger angle or from vertical to the pixel?
This is something which can also have an effect. Okay, I'm not an expert on detectors. Okay, but certainly there are maybe dependencies not only in angle of incidence but also in polarization. Okay, indeed, this is always taken care of in our measurements, and we always illuminate detectors with the same polarization. Okay, not to get rid of these spurious effects, but these variations with the angle do not only affect the detector itself. They also affect the filter graph. In the thesis of Fran, we have been analyzing many other, but in particular these effects of the angle of acceptance in the instrument. So you not only reduce your spatial resolution, but can introduce spurious effects. This is very true.
More question in the room or in Zoom? If anyone at the Zoom want to ask a question to Jose Carlos?
Thank you,
Enrique.
thank you, Enrique.
You mentioned when you mentioned the exposure time, you said that you want to reach a compromise so that the sun is the same within the exposure. Could you elaborate on the philosophy of that?
This is our daily problem. So I can go to an example. So today we are finishing the commissioning of two Magen skip instruments, which will have first light tomorrow in Kiruna, Sweden, before launch. That hopefully this time will take place by early January. Okay. 2MAG is based on filter graph, so that we have to tune across the spectral line in several wavelengths and take 4 measurements in order to derive the first those parameters. Then it takes time. It takes time. So our design is for 2MAG to observe 2 such spectral lines similar to the ones I shown you at 9 minimum wavelengths each in less than a minute. But we know that in that minute, sun has a period. So the first wavelength is taken when the sun is different to the last wavelength. And we have to survive with this. Which kind of trade-off we do? We say, well, if the typical variations in spatial variations across the sun are related to motions of x kilometers per second, typically 2 kilometers per second, okay? And my pixel takes, I don't know how many kilometers over the sun, then the typical time scale associated to that typical variation is that. Then by doing this, by selecting 1 minute for the total time of my measurement, I'm throwing out any faster phenomena. So I'm averaging everything which is below my observation time scale. However, if I was clever enough, I can take care of those important phenomena taking place slower than my time. But this is the only thing we can do.
I'm sorry, I have to say this. And we decline last. Now, just about what you just mentioned, you mentioned at the beginning that either you scan in wavelength or you scan long sleep type and scan spatially.
Yeah.
Now, in nighttime astronomy, there's been now like 2 decades at least that were reached. We're using a different technique and we get everything at once.
IFUs.
IFUs, yes.
Yes. Yeah. IFUs are not yet used in spaceborne or aerospace-borne solar physics, and it's only starting in ground-based solar physics. Now the best. Also, 20 years ago or something like that, they started in Hawaii, but so far, correct me, David, if I'm wrong, but so far the most performant ones are those made in the ISC for the European Solar Telescope. Okay, so there are plans to include this but the challenges are bigger. Okay.
But this is a question of the field of view that could be about.
This is a question of the field view. This is a question of spectral resolution, which we need a huge spectral resolution as compared to yours. This is also a matter of polarization, which has also a role in there. And well, in the end, so imagine, I've been saying that we are making observations which are photon starved. Then why don't you go to big telescopes as for nighttime astronomy? Because the technological challenges are much higher. So we are photon starved because we are looking at the very small details. We are having resolutions of a few milliangstrons. We have a special resolution of a few tenths of an arc second. And then this obliged to have obliged to get rid of 99.99% of the energy, which is concentrated by the primary neuron. And this is technologically unfeasible right now. Okay. So our analysis is much more detailed, and then there are developments that lag behind the nighttime developments. On the other hand, the knowledge we acquired in solar physics is of much application for nighttime astronomy as well.
More questions? Anyone from Zoom? Okay, no. Thank you again, Mr. Carlos.